Hello, I'm John Ploshnitznik, and today we'll talk to you about the data you just downloaded for Project LOCH NESS. So by now you should have already downloaded all that information tied to Project LOCH NESS and saved it on a location on your machine. It's about 30 gigabytes of information spread across 5 separate folders. It probably looks something like what I have here on my screen under my one Project LOCH NESS file folder. Folders 2 and 3 contain all of the raw data, the vehicle data and also the scene data. So let me go through and discuss what is in all 5 folders to help you out with looking at the data and understanding what is inside that data set. Under descriptions, you'll see 3 main folders. One talks about the Excel spreadsheet. It's actually all the content across all these folders, gives you file names. So if you're looking for anything, you'll have an idea of where something may be located. The Project LOCH NESS intro video is the one that you just saw on our ANSYS landing page for Project LOCH NESS. And last of all, the Project LOCH NESS presentation is a high-level presentation about what we're actually doing with Project LOCH NESS and why we have this data set provided to you as a AI, ML, or artificial intelligence algorithm developer. So that's the first folder. The next folder is going to be next 2 are 2 and 3. Let me come back to them. Okay, well, maybe I'll hit them now. So, folder 2. Folder 2 contains all the subfolders tied to each of the vehicles and also additional video targets or the video vehicles for each of the data scenes. So let me just show you what that entails. We'll go into the large aircraft, Project LOCH NESS large aircraft folder. Inside this folder, you're going to have image data sets and raw data sets. These are HDF5 formatted data. Each one of the HDF5 image files is collected at one of the 7 elevation angles, ranging from 30 to 60 degrees, so 7 different elevation angles. And in each of those files, we have 72 images. Basically, every 5 degrees around a 360 degree view along that elevation path. The raw radar data corresponds to the image data. It's going to be the frequency response data for each image. Will have a set of frequency response, responses over that image itself. So if you want to process that data, you can process it also. Remember, the goal of this effort is to allow you to not only deal with the image data, but also deal with the raw data. Because I don't know what kind of algorithms you want to try out, but you'll have that data. You can try different things out, and these are the radar data sets for the vehicles, which will be the targets that we're eventually going to put into the scenes that you're going to try to find. So the goal of this data here is to help you train your artificial intelligence algorithm with a lot of information. You can, with your HDF5 reader or MATLAB, go inside there, recreate the images, just reading them, or you can also go inside there and produce them yourself, maybe with your own algorithms. I'm giving you full flexibility to play with that data any way you would like, structure it any way you like to feed your algorithm and train your algorithm so that when you try to use your algorithm in the large scene where I have all those vehicles, will your algorithm work? So training and then the scene data can be used for testing or validation. So again, every one of the vehicles has these 7 different elevations, image data, and raw data files. So if you want to know how to read that data, let me show you. Let's go back to the Project LOCH NESS folders. Down in the support information, we actually have software detail. Under software details, we have a Word document which breaks out, basically gives you a description of all the fields in the HDF5 format. So when you have your reader and you look inside there, you'll know what content is available to help you understand what's going on in each of the scenes. During the presentation today and also the next few presentations, we'll talk about how we actually made the data. So you got a better feeling about, why did you pick this elevation, the azimuth, what do I actually get at each image. Okay, we'll talk more about that in these future videos I'll be producing over the next few days. And also we'll provide a HDF5 format description, a PowerPoint PowerPoint slide that will allow you to go ahead and see more details about the actual structure. There's some recommendations in there about using MATLAB and also using Python scripts to be able to read that data. So you have multiple ways of reading that data for all the vehicles and also for all of the scenes. Let's go back again and continue on with the directory definition. So back to the vehicles, you already saw if you go into the vehicle directory, we have each of the data files for each of the 5 vehicles, the large aircraft, small aircraft, helicopter, the fire truck, and also pickup truck. But I also give you a video directory of all that data so you can get an idea of what actually is in each of these data files. So I'm going to hop into the video directory, and again we have 7 different elevations. Let's go into 30 degrees. What you're going to see for each of the targets is 3 separate videos. The first one is the actual viewing geometry as we fly around that target, the scene, whatever it's going to be, right there at that elevation, and you're looking through the sensor and you may have a question about how is the vehicle oriented relative to me. The time steps in the video correspond to the azimuth location. So 0 ends up being nose on, looking at the vehicle. So the front of the vehicle, front of the aircraft, front of the fire truck, front of the pickup truck. And you'll go around 360 degrees at each of the different elevations. So in each of those folders, you can see how the vehicle looks to the collection system. I also have a radar X image file. And let me show you what that looks like. Okay, this is going to be an actual view of the data that is in the HDF5 data format. Remember, everything was collected at X band, also at 500 megahertz bandwidth. That gets you about purely a 30 centimeter resolution, but with a hand weighting that I incorporate in the data set, it'll be about 50 centimeter resolution. All right, let me go ahead and move some stuff around here. And the last one lets you go ahead and look at the target with the image. So you'll see when you look at this data file, you'll actually have the vehicle itself under the image, so you can see what could be the cause of various scattering sources. Just so you know, I used single bounce. I did not want to incorporate any higher order scattering. I can, but for right now, let's go ahead and make sure you get the primary scattering from all those vehicles, because that vehicle in the scene data will also be generated the same way, single bounce data. In the future, if you want to know more about that, there's a way to go ahead and turn on multi-bounce, as many as you want. If you want to look at dihedral effects like the back of the pickup truck, or even cavity response if you had any kind of open aperture where energy can go inside, be trapped, and come out in delayed time. Okay, so the structure for every vehicle is the same way. An optical view, I'll show you that real fast. You see how we're illuminating the vehicle. We also happen to have the radar view, and the radar and I refer to as target actually is the vehicle. For every one of the vehicles at this elevation, if you go back to the video targets folder, you'll see every elevation. Like 60 degree look down, you're going to see it looking very, very steep bank looking down. Now here we are, ready? Here looking almost on top of the fire truck as I am shooting it with the radar. And the radar image will look like this. So feel free to peruse through there and get a better feeling for how the scattering actually happens on this vehicle. This is a about 30, I think maybe a 20 meter vehicle, but I'll have to get that information for you. But that just shows you the scattering characteristics of that vehicle. As you move around on the bottom side over here, you can barely see, but this is actually the seconds for the video that corresponds to the actual elevation or actual azimuth of the collection. So video targets, and then we'll go to back up and go to the actual scene data. The scene data is from 3 different areas. One's the AGI headquarters, one's a city model, and one's actually a stadium. The city is actually of Denver. The stadium is the Denver Stadium. And again, corresponding videos to see what's inside. You have the exact same format for the scenes as you had for the vehicles, right? So we only did the collections for the scenes at 35, 45, and 55. And in each of the elevation cuts, I only did collections every 30 degrees. So it's only 12 images. The goal is to provide you a robust set of data at different viewing geometries with the targets inside, so you can test out your algorithm once you trained it with the actual vehicle data set. So here's some of the videos just to get a better view. So we'll go to 45 degrees. I'll actually go to 35 degrees. And let's go ahead and look at the AGI headquarters. Now, the optical view is also the illumination direction. So let's go ahead and look at the actual scene data. So here is the AGI headquarters every 30 degrees. And in this scene, okay, here's the scene itself. I'm going to show you the scene with the targets also inside. Let's put the targets inside there. And I even annotated it so you knew which targets were closest to me, which ones are furthest away from me, which one should I see first in the data. And I have, in most of the scenes, I have about 10 vehicles, but I do have a spreadsheet which identifies the vehicles that are in each scene and the locations of those vehicles in each scene. And again, the corresponding radar data, I gave you a lot of information. Basically, the radar view here, when you see radar and the scene, that gives you an idea of the radar model orientation that's going to correspond with the actual radar image. So let's look at the radar image first. Number 4 is a radar image. So this is 35 degrees, that same scene, and that is a collection. You can see where the shadows are. The aspect angle for this video is the radar image is on top with the range going this way, further away from the radar. And you see positive Doppler and negative Doppler with this aspect angle. You can do it any convention that you want. The raw radar data will actually have the radar looking from the bottom upward, and the negative Doppler will be on the left and positive Doppler will be on the right with that aspect angle. You can even see some of the vehicles inside there. 2 large aircraft, a small aircraft, and even the vehicles are smattered throughout that scene. And then I even give you the scene of this AGI headquarters, where you will see not only the radar image, the scene behind the radar image, and the vehicles also. They're actually physical models of the vehicles and annotated, so you know in your radar image where those vehicles are located. And again, please, feel free to go ahead and peruse through there, get a better understanding of what's happening in each of your radar scenes. The goal here is to provide you ground truth. When you get radar imagery, many times you won't have any information about what's inside, and you're being asked to find those targets, and then turning it over to an artificial intelligence algorithm gets to be very, very difficult unless you know precisely where something is with a training data set. But if you don't know where the object is, the overall goal is, will your artificial intelligence algorithm find those targets that your system was trained on? I'm creating for you a data set where you have full knowledge. You know exactly the vehicle that you have training data. You have exactly that same vehicle, that same facetized vehicle in the actual scene. So the scattering response will be very similar in that scene, except for the fact you may have a different viewing geometry. It all depends on how you're training your algorithm. All right. Let's go back out of here. We saw the videos. We saw the scene folder. Let's go back to the ground truth. The ground truth gets you all of the geometry information, and also when I look through the data set to try to help you out with that also. Let's go ahead and look at the locations of the targets. So this is a spreadsheet. If you scroll up and down, here's where I identify each of the three scenes. Here is where the target is located in meters relative to the center of the scene. And I provided some pictures for you to show you where the center of that scene is. Okay, you'll see over here the axes X, Y, and Z, and it tells you where that vehicle is in the large city scene. You can see I didn't include two large aircraft in the city scene, and I only used one small aircraft. I used two helos. I used 3 fire trucks in that scene and 2 pickup trucks. In the stadium, same thing again. Here's a list of vehicles I put inside there, and I identify which vehicles are inside there and where they're located. And then last of all, you can look at the scenes to see how it's oriented, the axes. And when you see it in the image, you'll be able to see where the object is. Stadium, and last of all, the AGI headquarters. Let me close that. And also I identified something extra for you. When you look at each of the 30 degrees, sometimes you have line of sight blockage. In other words, a building's in the way, or it's tucked too close to another building where you just can't see the full object. I try to identify the full blockage, partial blockage, and also on the actual data analysis portion, sometimes you have an effect called layover. Even though something could be visible to the radar, when you process the data, you'll get returns from the object, but you also get returns from parts of the scene. In the high rises, you get significant layover. You get returns from the front of the building, the illumination side, that may line up precisely with the vehicles also in that scene. None of my vehicles are moving. Everything is stationary, so there's no Doppler effect in this specific data set. In the future, we can go ahead and actually show you how Doppler will be properly mapped to the right cross-range bin based on the motion of the vehicle. For now, everything is very, very simple. And here's kind of an example of what we're talking about. Now, observability, let's open that up. I'm going to show you what that looks like. So inside here, I've identified for you the stadium, the headquarters, and also the city models. I've identified, like in the city, I mentioned before, the large aircraft were not inside there. But I tell you, at 35 degrees, 45 degrees, and 55 degrees, whether or not that one small aircraft at each of these azimuth locations, is it being illuminated? And will you see it in the data? Because I looked at all the data sets to see. So in this case here, you'll see, even though in this case, when you have no illumination from because it's being blocked, you're not going to get any return at all in the observable portion of the image. So here you see its illumination. You can see the object inside here. Here you may see illumination, but you may have some partial interpretability. In other words, maybe there's layover or whatever the case is. It's obstructed in the actual scene. You should see it in your data. I'm just giving you a heads up what's going on. And also you see right now for all the vehicles, I tell you how you're illuminated and how you may want to interpret that data. And the city has a lot of line of sight blockages and a lot of layover. Like for instance, the helicopters, they're on top of the buildings and then you have a lot of layover, so it's really hard to pull out the helicopter. Maybe your algorithm has a way to pull it out of the raw radar data, but right now I'm just telling you visually, you're going to have a very difficult time trying to find those helicopters in the city scene. So that's just my visual observation looking at that data. Maybe you see the same thing, or maybe you have some brand new algorithm that can find those vehicles that you trained your algorithm on. Maybe you have some special algorithm dealing with the raw data. If you can find it in the raw data of the scene, be very impressed. I think people will be very happy to see your results. Let me close this one. And here's a couple examples of what I'm talking about with observability. So let's go ahead and look at the helicopter. Okay, the helicopter in the city, again, it's a true nightmare. And again, here are the viewing geometries. The viewing geometries are 35, 45, and 55. I just replaced the actual different scenes, the AGI headquarters, the city, and the stadium in the collection location, and I flew around there every 30 degrees. The actual targets were collected every 5 degrees at 7 different elevations to provide you a very comprehensive data set of the scattering characteristics of these objects in a similar, horizontal alignment orientation. If you ever wanted to turn this around and look from the ground up, you would have to look at these vehicles and save data in many different aspect angles. We can do that also, but right now we're focusing on the SAR scenario where there's a lot of focus on artificial intelligence trying to find targets in these very large SAR scenes. Okay, here again some more information. Here's an example at 35 degrees. Look at these targets. You see, here's how I'm illuminating the helicopter on top of a building. The radar image, okay, for this right now, here you see the helicopter inside there. It's actually a radar looking from this direction down. You see the extent of the layover. It makes it very difficult. If you look very close, you will go ahead and see the blades in here, but it gets to be very, very difficult. Again, same building. You can see how hard it is because the returns from this side of the building happen to fall into the same range and Doppler bin and has a lot of layover. Makes it very difficult to find those objects. So the helicopter, I'm giving you the worst case scenario in this specific scene to try to go ahead and use your algorithm and hopefully successfully pull that out. I wouldn't be too optimistic that's going to work. I'm going to walk around here different ways, different scenes. Then we're going to hop on a different aircraft. Let's go ahead and look at a different scenario. Okay. Let's go ahead and close this one. And I'm going to show you the small aircraft. Small aircraft, same presentation structure. Go to the full scene. Here we go. Same series of slides explaining what's going on. 35 degrees. Here's the aircraft on top of a flat building. Okay, here's how I'm illuminating it. You see the left wing, I should be hitting first. According to the radar, the left wing is what I am hitting first. And you also get the shadow from the vehicle and with the return from the top of the building. So as you walk through here, there may be some very good data you can get out of this and be very fortunate in your collection. This is an artifact of our photogrammetry data because I'm able to look through the back side of the building, but the reality is the facets for the front of the building actually masks the aircraft. That's why you're not seeing the aircraft in this scene. I also annotated in the spreadsheet the same way. You can see now I'm illuminating the back of the aircraft first. The radar energy at 35 degrees illuminates the back right tail first. So this may be very, very promising. And again, the actual response that you're getting from this aircraft is due to a facetized model in that we also generated the same radar data independently without the buildings. Okay, so the goal is, can I train it on a very good data set so that you can develop your algorithms, see how it's able to learn about those signatures, and then applying that artificial intelligence algorithm against its large scene. It's a much larger data set. I could expand this out very, very big. But right now, I want to get and zoom in to where the aircraft was so you can see what it looks like. I would have loved to do this for every vehicle and every scene, but this is very time consuming. I just want to go ahead and give you a little bit of insight into how I developed the information or the content for that spreadsheet. All right, we'll step through here. And these returns here, basically, you're seeing here is the front of the building. This is the energy hitting this portion of the building. And you're seeing the way the vehicle is aligned. This is actually the front of the vehicle. These are the trees. And this is going to be, you see, front leading edge scattering of the right wing. Appears right over here. So I don't know what your discriminators are. I don't know how your algorithm is being trained, but you do have the data set for this vehicle that corresponds to many different angles, 7 different elevations, many different azimuths. Hopefully your algorithm can be trained to find these vehicles in corresponding scenes. Remember, these are the exact same vehicles as I provided for you for training. All right. So that completes that. Okay, so now we finished up, the ground truth data. So you will have full confidence on what can be seen and what can't be seen. Now, in our tool itself that we use to generate the data, we have the ability to analytically do this very, very fast by zooming into the specific targets. But for you right now, consider this: you're being provided data for training, you're being provided data to be used for validation and testing. Ultimately, you would hope to have a great signature from a source. Maybe it's a test range that was measuring, and you train your algorithm. Will your algorithm work against that target in a real SAR measurement, like from Capella or ISI or Umbra, right? That's the game plan. And last of all, I mentioned support information already. That support information has additional information about the actual model details, right? So in this case, the models, when I look at these right now, you'll see the little video to kind of give you a little bit more details about what could be scattering features. These are purely informational videos about the 5 different targets. Looking at the helicopter, you can see what it looks like. All right. And also, we'll go ahead and show you the scenes too. Here are the actual scenes. And I also provided a little bit information about the source of the data we have for the city and the stadium models. The city model that you see here came from a company called Aerometrics that generated this photogrammetry. It says 5 cm resolution. Here's that building I mentioned before, that kind of looking through the backside of the building. As you see, as I move around, you can see that actually blocked the aircraft down in this area. But this gives you realistic, facetized scattering points that are totally consistent with what actually is going on in Denver, except for the fact that this was created on a certain date. Since then, things may have changed. And I have data that actually shows how that appears in real data when I look at the Denver stadium scenario. So the goal was to create realistic radar data, put targets inside there, put the helicopters inside there, put the vehicles inside there, and see when the opportunity or the viewing geometry exposes that vehicle, will your algorithm find those vehicles in this very, very dense urban environment. The stadium, I have just a metallic model of the stadium here. Again, from the same model set, I created a GLTF data set. And I think, let me see, I have the aircraft. No, I don't have the aircraft inside here, but this shows you certain features, roads, and also, just so you know, right now we're only using one material for the entire data set. We're actually exploring the ability to assign material content like for roads, vegetation, concrete, steel, glass. That's coming in 2025. But for now, everything is one material. So don't be too surprised if the response you're getting from what appears to be grass may be brighter or darker than you would expect. Main thing is, there's a vehicle in this specific area. Will your algorithm find it? And last of all, the AGI headquarters, which was created several years ago from one of our engineers. And last of all, company information. Aerometrics actually generates this data, beautiful data, 5 cm, 2 cm, and even street level data, from camera data to where these models are so realistic they can be used for trying to train optical sensors for artificial intelligence algorithm generation. And I think the collection geometry information, this is related to, remember I showed you the different elevation collections? This is the details about how I'm flying my sensors around the targets or the vehicles and also the scenes. So this gives you all of the Cartesian coordinates around the center of the scene, and in that other spreadsheet I show you where that center is in the scene. And this is how the vehicle is flying a nice, beautiful path for 30 through 60 degrees. And I use this information, the exact same viewing geometry, for both the targets or the vehicles and also the scenes. I think, let me see here, Davis. This is an example of, again, the viewing geometries that we have that ephemeris data for. And remember, in this case, these 5 targets were basically being measured one at a time at each of the elevations and at 72 separate azimuth locations to generate the corresponding images, so that you can go ahead and use either the images in the HDF5 format file, the image is in the name, or we also generated the raw data for each of those vehicles. So basically you're getting all the raw data. If you want to process it yourself, please go ahead and feel free to use your own algorithms, use your Fourier transform algorithms, use your back projection, whatever you use. Feel free to go ahead and use it, and use that to go ahead and test and develop your artificial intelligence algorithm. And I think that is all. And software details, again, HDF5 format data to help you actually read the HDF5 format files. What we'll do is probably create a user group maybe under this. I'll think about that. Maybe as people find things out, you can share information, share that content with other people who are trying to go ahead and exploit this data and develop new algorithms. The goal is we want to show you what can be done with synthetic data. Remember, we're not using the synthetic data that we have here to train artificial intelligence algorithms against real data sets, because those models are probably too low in resolution to generate realistic response that would be consistent with the real vehicle, aside from the fact that we don't have the full material characterized, and also many vehicles have apertures which give you unique scattering effects. And I want to make sure that we, first of all, does your algorithm respond to training from a vehicle that will also appear in a realistic data set. All right. So I think that's it for now. I hope you enjoyed that. If you have any more questions, please just go ahead and send me an email, and we'll try to go ahead and respond. And I'll be following up with 2 more videos. The first video, I referred to it as making the sausage. Okay, we're going to go ahead and teach, or at least show you, how we generated the vehicle data and the vehicle imagery, the raw data, and we'll also show you how we generated the scene data with all the vehicles inside, and I can show you how we actually did that with our tools. All right, so thank you very much. I appreciate it. Have a good day. Goodbye. And thank you for participating in Project LOCH NESS.